Alright, so good day everyone. Today we are going to learn right hand grip rule. But first and foremost, I need to tell you what are some of the directions normally that will come out in our examination. Okay, the first one is you go upwards. The second one is you go downwards. The third one is you go to left. The fourth one is you go to right. And the fifth and the sixth ones are either out of page or into the page. By the way, do you know why we use a dot to denote the direction out of page? It's because of the arrow. Okay, this is an arrow. If the arrow, is moving towards you, that means it is coming out of the page and then towards you. Alright, so we put a dot there because it looks like a dot here. Okay, it looks like a dot here. But now, if you are the one who shoots the arrow, okay, you shoot the arrow, so you can see that the arrow is moving away from you and then going into the page. So you can see a cross here, right? And that's why we use the cross here to denote the direction of into the page. Okay, or you can say that into the plane of page. Alright, so after you know the direction, it's time for us to learn about right hand grip rule. Now, please find the direction of the magnetic flux density, or maybe you can say magnetic field, for a straight current carrying conductor. Okay, so for example, this is a wire, and then this wire carries a current. The current is going upwards. Now, when you use a right hand grip rule, please make sure that you use your right hand. If you use your left hand, then everything is totally wrong. Okay, so make sure that you use your right hand. Now, for your right hand, this is your thumb fingers, right? This is your thumb finger. And these four fingers, okay, you put them together. Alright, so this thumb finger should point along the direction of current. And then how your four fingers close show you the direction of magnetic flux density. Okay, so for example, this is 3D diagram, this is the top view, and then this is the side view. Now, you take out your right hand, okay, your right hand is here, and then, once again, you make sure that the posture of your right hand is like this. The four fingers must be together, and then your thumb finger is almost at 90 degrees with the four fingers here. So now, you see in this diagram, okay, your thumb finger points along the direction of the current. Okay, so your thumb finger is exactly the direction of the current. And then, what do? You close your fingers. Okay, you close your fingers. It should look like this. Okay, so now you should know that the magnetic flux density, or maybe the magnetic field, is like this. Okay, and then tell me the direction. Okay, it is what? It is anti-clockwise. Okay, it is anti-clockwise. This is the direction of the magnetic flux density. Okay, we use B to denote that. Now, if you look at it from the top view, okay, you look at this from the top view, you can see that the current is coming out of the page towards you. Okay, this is the top view. And once again, you use your right hand. Your thumb should point along the direction of the current, okay, which is towards you, out of the page. Okay, which is out of the page, the direction of your thumb, which is the direction of the current. And then you cross, okay, you cross your fingers. You cross your fingers. So now you should know that the direction is anti-clockwise. And then, normally, if you want to draw a diagram to show the magnetic flux density, please give me at least 3 circles. Okay, please give me at least 3 circles. And then normally the third one should be, much larger than them. Okay, and then don't label that this is the magnetic flux density. Okay, and then this is the direction of current. Okay, so I want to see the separation is increasing. All right, the distance between here, okay, the distance between here and here should be smaller than the distance between here and here. And the distance between here is also much smaller than the distance between here and here. Why? Why the separation must be increasing? Because if you know, okay, if you know the formula, you know that the B is inversely proportional to R. The R is the distance away from the wire, okay, from the current carrying conductor. Okay, so the larger the R, the smaller the B. And you know that when the field densities, are further away from each other, then I can say that the magnetic field density here is less stronger. For here, all the lines are compact together, okay? All the lines are very dense here, okay? So I can say that the magnetic field density is very strong here, okay? So now this is the side view. Once again, you use the right hand, okay? And then your thumb is moving along with the direction of current, and then you curl it up. This is the side view. This is a side view. So it will come out of the pitch and then into the pitch later on. Okay, so it should look like this. Okay, don't forget to label them. Okay, so this is the direction of the magnetic flux density, which is coming out of the pitch and into you. Okay, and then later on it will go into the pitch again. Okay, or you can do like this. Okay, into the pitch and then out of the pitch. Okay, so it is out of the pitch on the left hand side and then into the pitch on your right hand side. Okay, out of the pitch into the pitch. Okay, so now this is the current going upwards. Okay, this is about the current going upwards. So what about we change the current? Okay, we change the current. We want the current to be going down. Okay, so once again, you use your right hand. Okay, you use your right hand and then you move along with the direction of the current and then you cross a finger. Okay, you cross a finger. Okay, just now, it is what? It is clockwise. Okay, it is clockwise. Okay, it is clockwise. This is 3D diagram. If you look at it from the top view, okay, then you can see that the current is going away from you. Okay, it's going into the pitch. Okay, like this, going into the pitch. Okay, so now once again, you take out your right hand. Your thumb is going into the pitch, and then you cross a finger. So it is what? It is clockwise. Okay, it is clockwise. Okay, this is clockwise. If you look at it from the side view, okay, from the side view, okay, here is into the pitch, and then here is out from the pitch, okay, out of the pitch, and then here is into the pitch, here is out of the pitch. Okay, so once again, I use my right hand and then I show that, my fingers is going into the pitch and then my fingers are going out from the pitch, out of the pitch, alright? So it's into the pitch on your left hand side and then out of the pitch on your right hand side. Okay, so now, that's why when we look at this, right? If the currents, okay, if now you have two conductors and then all the currents are going in the same direction. So what you do here is, okay, for example, you look at here, okay, and then you imagine that the I1 is not here. You imagine the I1 is not here. Okay, I want to find out the direction of magnetic field due to I2, okay, which is B2 at this position. So you see, my thumb finger is the I2 now. I2 is coming out of the pitch. That's why I use out of the pitch here. Okay, and then the current I1 is going outwards. B2 is the magnetic flux density due to I2. I1 is the current of I1. Now, your Fleming left-hand rule, okay? Your Fleming left-hand rule. Magnetic force, magnetic flux density, current. Okay, so B2 is going out of the pitch. And then I is outwards. So that's why your F is towards your right-hand side. Now we look at this, okay? We look at this, okay? We look at the position here. We look at this dot here. If you imagine that the I2 is not here, okay? You imagine that the I2 is not here. For the I1, okay? For the I1, okay? For the I1, the magnetic flux density due to I1 is into the pitch at here. So that's why I said that the magnetic flux density due to current I1 is into the pitch at this position. Now the current I2 is going outwards. So once again, you use your Fleming left-hand rule to find out the direction of the magnetic force. B is into the pitch, I is upwards. Okay, so your force is to left. Okay, so in these situations, I can say that when the conductors carry the currents in the same direction, then the conductors will attract each other. By using your, Newton's third law of motion, F1 and F2 should have the same magnitude, but they should have opposite directions, okay? Because this is towards right and then this is towards left. And then these two forces are magnetic force, okay? Because for the Newton's third law of motion, it must be valid for the same type of force. You cannot say that this is magnetic force and then this is, let's say, gravitational force. Wrong. You cannot say that this is magnetic force and then this is electric force. Wrong. They must be of the same type of force. Okay, this is magnetic force and then this is also magnetic force. Now, if the currents are in opposite direction, okay, so we look at the position here. We look at the dot here. You imagine that the I2 is not here. Okay, you imagine I2 is not here. You look at I1. You use a right-hand grid rule. Okay, you use the right-hand grid rule. Shoo. You know that the magnetic field density, okay, magnetic flux density due to I1 here is into the pitch, okay? Because you see, it is going into the pitch, okay? It is going into the pitch, okay? It is going into the pitch. So B1 is into the pitch. Now I2 is going downwards. So by using your Fleming left-hand rule again, B is into the pitch, I is downwards. So your F2, okay, the force acting on this conductor, F2, magnetic force acting on this conductor, is to right. Now you look at this position. And then you pretend that, I1 does not exist. Okay, you pretend that I1 does not exist. You look at I2. By using your right-hand grid rule, okay, it is going into the pitch, okay? The magnetic field due to I2 is going into the pitch at this position. Okay, so that's why I say B2 is going into the pitch. And then now you see the current is going outwards. Once again, by using our Fleming left-hand rule, B is into the pitch, I is outward. So your magnetic force is, okay, to your left-hand side. F1 is to your left-hand side. And once again, you see this pair of forces obey the Newton's third law of motion. First and foremost, they have the same magnitude. And then they have opposite directions. And then they are the same type of forces. I mean, they are both magnetic forces. Okay, so conclusion is, if the currents are going in the opposite direction, then the conductors will repel one and another. Okay, so now let's move on to the solenoid. Okay, let's look at a solenoid. Actually, a solenoid is like a spring. Okay, it's like a spring. Okay, it's like a spring, a spring. It is exactly like a spring, but with current. Now, for example, if I want to conduct the battery like this, okay? If I want to conduct the battery like this, then this is the positive terminal and this is the negative terminal of the battery. So you know that the current is going like this and then come back. Okay, this is the direction of the current. Okay, now in order to find out the magnetic flux density of a solenoid, okay, then what do? You cut open it. Okay, you cut open it. You use a knife to cut open it. Cut. Okay, you cut it, and then this is your side view. Okay, you look at the current. It is going into the page and then out from the page, into the page, out from the page, into the page, and then come back to the battery. So it's like this. Okay, the current is into the page, into the page. The current is out from the page. Okay, out of the page. The current is into the page, into the page. The current is out of the page, out of the page. The current is into the page, into the page. Okay, so basically the current is like this. Okay, the current is like this. The current goes here, okay, and then goes here again, and then goes here again. And that's why, okay, the current is into the page, into the page, into the page, into the page, into the page. Okay, out of the page, out of page, out of page, out of page. Now, once again, by using your right hand grip rule, okay, because now you have the current, you have the thumb, and then you are going to find out the direction of the magnetic field. Okay, let's look at this. Into the page, okay, sorry, out from the page, and then out of the page. Then your current is going outwards, and then you curve your finger. You notice that, okay, the direction is towards here. Okay, once again, okay, you notice that the direction is to left. Okay, if you don't believe me, then we try out the current which is going into the page. Okay, we try out this. Okay, going into page, and then it's also going to left. Okay, I repeat, if you look at these two, then it's like this. Okay, so going to left. If you look at this tree, okay, which is going to left as well. Okay, so that's why we can draw the magnetic field or the magnetic flux like this. Okay, inside the solenoid, all the lines should be equally spaced. Okay, and then outside the solenoid, the lines are diverted. Okay, so don't forget to label. This is the direction of the magnetic flux density. And now, do you still remember what is a permanent magnet? Let's say you have a permanent magnet and then you have the north pole, you have the south pole. Do you still remember that, the magnetic field should come out from the north pole? Okay, come out from the north pole and then enter the south pole again. So let me ask you a question. Does a solenoid produce a magnetic field that looks like this? Okay, that looks like a permanent magnet? Yes, it does. And you see, from the north pole, okay, the magnetic field is coming out from the north pole. Okay, the magnetic field is coming out from the north pole. So we say that this is the north pole. The magnetic field will enter to the south pole. So we say this is the south pole because the magnetic field enters here. And if you notice, okay, the current is going like this, right? Okay, so if you look at this, this is like this. Okay, I mean the current, okay, the direction of current from here. If you look at it from the side view here, but if you look at it from the side view here, then it's like this. Okay. So next time, when you see the direction of the current, right, you already know that this is the north pole. Okay, this is the north pole of the solenoid, and then this is the south pole of the solenoid. Okay, so now let's try to reverse the direction of the current. Okay, so now I reverse the direction of current. Okay, just now the direction of current is like this. Just now is like this. Now I change it to this. Okay, I change the direction of the current. How do I change the direction of current? I reverse the polarity of the battery. This is positive terminal, this is negative terminal. Okay, so once again, the current will come out from the positive terminal of the battery and then into the circuit, and then finally it will enter the negative terminal of the battery. Okay, so now you know that the current, okay, will go like this. Okay, it will go like this. Okay, so what do you do here is you cut open the solenoid. Okay, you cut open the solenoid, and then the side view of the solenoid will be like this. Okay, you see, the current, okay, the current is out of pitch, and then into the pitch, and then out of pitch, and then into the pitch, and then out of pitch again. Okay, so now once again, by using your right hand grip rule, if you want to know the direction of the magnetic field due to the current. Okay, so let's look at these two first. Okay, this is what? This is into the pitch. Okay, into the pitch. So it is going to here. Okay, into the pitch. Okay, so here. Okay, into the pitch, and then here. For these three, they are out of the pitch. Okay, out of the pitch. Out of the pitch. Okay, so once again, it's going to your right hand side. And then what do we do here is we make sure that we can draw the magnetic flux. I mean all the magnetic lines beautifully. Make sure that you use a ruler, okay? Give me a moment, yeah? Give me a moment. Inside the solenoid, please remember that the lines must be equally spaced. Okay, the lines are equally spaced. And then outside the solenoid, then only the lines will diverge. Okay, they will go apart. And don't forget to label that this is the direction of the magnetic flux density. Okay, so now once again, do you remember what is a permanent bar magnet? Okay, a permanent bar magnet. This is the north pole of the bar magnet. This is the south pole of the bar magnet. If you remember, then the magnetic field will come out of the north pole, and then they will enter the south pole. Okay, they will enter the south pole. This is the magnetic flux density or magnetic field. You can check out my videos if you want to know the difference between magnetic flux density and the magnetic field density. Actually, they are different, but the direction of them are exactly the same. Okay, now if you look at it, does a solenoid produce the magnetic field density which looks similar to a bar magnet? Yes, it does. And that's why the magnetic flux density comes out from the north pole, and then the magnetic flux density will enter the south pole. Okay, so this is the north pole of the solenoid, this is the south pole of the solenoid. Okay, and once again, you look at the direction of the current here. If you look at it from this side view, okay, from this side view, okay, so they are, okay, the current will go like this, okay, will go like anti-clockwise, okay, from this side view. You look at here, and then the current is going like this, okay, anti-clockwise, so a north pole. And then if you look at it from here, I mean if your eyes are here and then you look at it from this side view, you will see that the current is moving like this, okay, which is clockwise, okay, which is clockwise. This is the direction of current, okay, this is the direction of current, and then this is an N, because this is a north pole of the solenoid, and then this is the south pole of the solenoid. Okay, so you look at this and then you compare with this. Just by changing the polarity of the battery, I can make sure the poles of the solenoid, they are inverted. Okay, they are inverted just by changing the direction of the current. Okay, so I think that's all for today. Thank you very much, and I wish you all the best. Bye bye.